Okay, good evening. Provost, Dean of Research, colleagues, visitors from outside, and members of Johnny's family. I would like to welcome you all here to the School of Physics this evening for what is a very important occasion in the year of the School of Physics, because tonight we're inaugurating Jonathan Coleman as a full professor in the School of Physics. Tonight, my name is James Lunny. I'm the head of the School of Physics here for 3 years. I'm standing in tonight for the Dean of Engineering, Maths and Science, because he's traveling, so I'm acting for him. So Johnny has been promoted to the most senior position, academic position in the university, before he has got to the age of 40, and this is indeed a great achievement. Johnny did his undergrad degree here in physics. He did his PhD in physics. He was supervised by Werner Blau, who many people know here. He then very quickly made his way through the academic ranks here, from lecturer to associate professor, and recently then has been promoted to full professor. He is the professor of chemical physics. I suppose this is reflecting that in these times subjects are getting somewhat mixed up, or what we call they're becoming interdisciplinary. So I think Johnny is one of those people. He's also what is called a principal investigator in CRANN, and what that really means is that he runs a large research group, he brings in a lot of money, and he publishes a lot of papers, and that's what it means to be a PI in CRANN. And you are also supposed to have I think it's called industry-facing research. So he does that as well. So he's a busy man, and if you watch Johnny, he's always running around. You can hardly keep up with him. So he's a young man in a hurry, and he's getting there. Recently his work has been on liquid processing of nanomaterials, and that's what he's going to talk about tonight. He has published 150 papers, and he's listed as he's listed in the top 100 material scientists in the world. So it's a great achievement for Johnny, but it's also a great achievement for Trinity and for the School of Physics and for CRANN. It seems to me recently that Johnny's face is everywhere. And I thought that when I would escape to the foothills of the Dublin mountains, that I would get away from Johnny. But it's not the case. Our local community magazine called Three Rock Panorama. So open that up, and who do you find but Johnny Coleman? So I think he has really made it. So now I would like to invite Johnny to present his inaugural lecture, Tiny but Mighty, How Today's Nanomaterials Will Lead to Tomorrow's Technologies. Johnny Coleman.
Well, thank you very much, James, and I must say those were my thoughts exactly. When I saw myself in Three Rock Panorama, I knew that this was it. And I must say that it really gives me great pleasure to be here today, because this is the lecture theatre where I learned physics as an undergrad from many of the people who are here today, and where I now teach physics to the undergrads of today. So it's really nice to do this here. So I'm going to talk to you today about my research. And the title of the talk is Tiny but Mighty, How Today's Nanomaterials Will Lead to Tomorrow's Nanotechnologies. But I recognize that this is a somewhat open audience, so I'm not going to focus on the complicated stuff. I'm going to try and start off at the beginning and bring you right into the research. So I'm going to introduce nanoscience and nanomaterials, which are what we study here, certainly in CRANN. And then I'm going to talk a little bit about my own research, and then I'm going to try and show you how this sort of research can be developed into, hopefully, industrial products. So first of all, for the people here who aren't scientists, what is nanoscience? Well, I mean, it is really what it says. It's the science of very small objects. And typically, that means less than about 100 nanometers. And a nanometer is a millionth of a millimeter. So these things are really, really small. And nanotechnology deals with engineering nanoscales for functional usage. And what that means is to make things, and to make things that will ultimately be useful. So why would nanoscience be of interest in more general terms? Well, first and foremost, it's interesting because it's new. It's really at the edge of the envelope of science, and it's only in the last few years that we've learned to manipulate materials on these very, very small length scales. But on a more practical front, it's interesting because materials tend to behave differently when they're small. And ultimately, that may lead us into new applications. So an example of this is the so-called silicon nanoharp. Now, this is something that was originally a lump of silicon, and bits were cut out of it using a process called lithography and then etching, and it was cut into the shape of a harp. And this bar here is 1,000th of a millimeter. So this thing is pretty small. And these so-called strings can be plucked and they vibrate. But because this is so small, the vibration frequency, how fast the strings vibrate, is about 1,000,000 times faster than a normal harp. So that gives you some idea how the properties of materials and structures change when you make them very small. And there are probably many, many ways where we can use that. So how small is small and how small is a nanometer? Well, I've already said that a nanometer is 1,000,000th of a millimeter, but it can be difficult to grasp how small that really is. So to try and give you some idea, let's look at a series of photographs. So this is an oak leaf. So this is something, the photograph is 10 centimeters wide, and this depicts something that we would all be familiar with. So let's zoom in to the center of that so that we zoom in by a factor of 10. Now, when we do that, we start to see the veins in the leaves, and we start to see some structure in the green part of the leaf. If we zoom in again by a factor of 10, you see that there are little lines and markings on the leaf that you would find it quite hard to see with the naked eye. You zoom in again by a factor of 10, and even inside those lines, there are these circular type of structures. You go in by another factor of 10, and you see there are still smaller circular structures, and these are the cells that the leaves are made of. Now you go in yet again, and you see the cell nucleus. And this image here is 1,000th of a millimeter wide, which is a micrometer wide. You go in again, and you see the chromatin, which is inside the cell nucleus, and this is a combination of DNA and proteins that is arranged to keep the DNA compact so it'll fit in such a small space. And then you go in by another factor of 10, and you can see the DNA inside the chromatin. And then you go yet another factor of 10, and you can see the structure, the base pairs of the DNA, and that is 1 nanometer. So this is really, really far away from the length scales that we're used to in everyday life. And we shouldn't be surprised if things are a little bit different down there. So let's put it another way. Here is something that is on our length scale. It's a football. Now, we would all agree, I think, that the difference in size between a football and the Earth is pretty big. In fact, the Earth is about 100 million times bigger than football. And within our everyday experience, that is a very big difference. But let's look at the other direction. So if we go 100 million times smaller than a football, we get down to an object which is 1 nanometer in size. And this is a molecule, a carbon-60 molecule, which is on the bridge between molecules and nanostructures. So this structure at the nanoscale is as different to things that we experience in everyday life as our everyday experience is to the size of the world. So really, this is very, very far from our everyday life. So nanoscience deals with the very, very, very small. So let's look at some examples of nanomaterials. So this is the carbon-60 molecule I showed you before, just 1 nanometer or 1,000,000th of a millimeter across. This is a really, really small piece of gold. A piece of gold such that it's only a few nanometers across. And this is called a gold nanoparticle. And immediately you can see one difference between the everyday life that we know and the nanoscale. This gold nanoparticle is a particular shape, and that's not a random shape. That is a special shape that's governed basically by the fact that it's so very small. Now, these are small structures, but we can also control the structures that we make. And this is the silicon nanoguitar, which was cut out of a piece of silicon using lithography and etching. And this wasn't made for any particular reason other than to demonstrate the power of today's technology and to show what we can do. Now, of course, there are different ways to demonstrate that technology, and everyone has their own idea. But I think the message is that you can really do a lot of stuff nowadays, and there is scope for us to really control matter at the nanoscale. This is another nanomaterial, the carbon nanotube, of which I'll talk a little bit more about. So there's a whole hierarchy of sizes of these nano-objects. The smallest things at the nanoscale are about 1 nanometer or a millionth of a meter in size. Carbon nanotubes have a diameter that can range between maybe 1 nanometer and a few tens of nanometers. But the length of carbon nanotubes, their long objects, can go from about 100 nanometers up to centimeters. So in some sense, these carbon nanotubes are linked to the nano world. They have one dimension, their diameter, which is in the nanoscale, but their long dimension, their length, can be long enough so we can really appreciate it. And just to give you some idea of, well, these things are very long. I'll show you in a minute. Now, it's interesting. It's not really relevant, but it's interesting to note that these length scales are the same as the smaller length scales in biology. So, for example, the 1 nanometer length scale is more or less the size of a DNA base pair. Tens to hundreds of nanometers, you have viruses. Micron size, you have bacteria. Tens of microns, you have pollen. And maybe 50 to hundreds of microns, you have hairs. So really, there is a lot of overlap between these nanoscale objects and these bio-objects, and of course that immediately suggests that you can do bio-nanotechnology, but that's not something I'll talk about today. Now, another thing that's important to note is that all of these things, these nano-objects here and these bio-objects, are predominantly made of carbon. And that's not by chance. There's a reason for that. And it turns out that carbon is a very, very special element. And the reason it's so special is because of where it sits in the periodic table. This is a unique site in the periodic table because it means that carbon can bond to other structures in some interesting ways. So just to show you, carbon can bond to 4 other atoms, in this case methane, where the 4 bonds point in all directions. So the bonding is 3-dimensional. Or carbon can bond slightly differently to 3 other atoms, so the bonding is in a plane, i.e. 2-dimensional. Or carbon can bond to 2 other atoms, so the bonding is in a line, is linear or 1-dimensional. Now, these are all, to the chemist, certainly familiar molecules, but what's interesting for us is that these bonding schemes can be continued to fill space in 3 dimensions, 2 dimensions, and 1 dimension. So to give you an example of that, this is what happens if you take a carbon atom and bond it to 4 other carbon atoms in 3-dimensional space. You have diamond. If you take a carbon atom and bond it to 3 other carbon atoms in a plane, you have something called graphene, and many sheets of graphene stick together to give graphite. Or you can have carbon that bonds almost in a linear array. People actually haven't managed to get linear carbon. The nearest they've got is this molecule with iodine attached, and anytime people have tried to remove the iodine, basically the lab explodes. So this has been known for about 30 years, and people are quite happy they're not going beyond that. So let's have a closer look at this stuff, these 2-dimensional sheets of carbon. Well, 2-dimensional sheets of carbon are known as graphene, and actually for a long time it was believed that graphene couldn't exist away from its parent crystal of graphite. But in 2004, 2 physicists from the University of Manchester showed that that was not the case, that the sort of received wisdom was wrong. They discovered you could make individual sheets of graphene, and furthermore, they discovered that this graphene had some really wonderful physical properties. And for that, the Nobel Prize was awarded in 2010. So I want to look at this stuff in a little bit more detail. So if you take a sheet of graphene, it's just carbons arranged like chicken wire, and it's a 1-atom thick sheet. And one of the reasons this material is important is that this has been called the mother of all carbons. It's been proposed that you can get any sort of carbon out of it. So for example, if you cut a load of slices of graphene and stick them on top of each other, you have graphite. If you take a rectangle of graphene and roll it up, you can imagine a cylindrical form of carbon. And if you take a certain funny-shaped piece of graphene with 60 atoms and roll it up in a complicated way, you can get a sphere. Now, it was known for a long time that these sort of transformations of two-dimensional carbon were possible. But these sort of objects hadn't been observed, except for graphite. And then in 1985, things really changed because a new form of carbon was discovered, which is C60. And C60 is just 60 carbon atoms arranged in a sphere, a bit like how old footballs used to stitch together. And this was first observed not on Earth, but spectroscopically in interstellar dust. And the important point about this molecule was that it showed that new types of carbon other than graphite and diamond were possible. And that really opened up people's imaginations, and they thought, well, what else is possible? So for a long time, people wanted to try to make C60 in very, very large quantities, and people were making all sorts of complicated apparatus to try and make C60. And then one day in 1990 or 1991, in one of these apparatus, people were making black powder, and then they were looking at the black powder with electron microscopes. And what was found in the electron microscope were these objects that it became pretty clear pretty quickly were some sort of cylindrical forms of carbon. And immediately, almost immediately, people realized that these things could be useful. They realized that they were somehow related to graphene, they were long, they were thin, and they might be good for something. So what's their structure? Well, you take a piece of graphene and you roll it into a tube. Now, the interesting thing about this is that depending on how, there isn't just one way you can roll up the tube. You can roll up to form a tube one way, then you can imagine opening it and rolling it back together at a different angle, and you get a slightly different tube. Now, the reason that's important is that depending on the angle at which you roll the graphene sheet into a cylinder, you can have materials that are metals, that are semiconductors, and for the semiconductors, they can have a wide range of band gaps. So immediately, just with this simple piece of carbon, you've got the whole range of possible electronic structures. So at that point, people realized very, very quickly that these things are exciting, because that's the sort of thing the likes of Intel, really want to see. So how do we make them? Well, at the start, they were made sort of by accident, but very quickly people learned how to do it. And this is a movie taken in an electron microscope showing the growth of carbon fibres. Now, these are not carbon nanotubes. They're much bigger than carbon nanotubes, but the growth mechanism is the same. Basically, you have a piece of metal catalyst, and you have a very, very hot gas. The gas goes into the metal catalyst and is pushed out the side to form a tube. So just to show you, you can't see the gas going in, obviously, but you can see the stuff coming out in a tubular form. Now, for carbon nanofibers, the tubes are very disordered, but if that was a single nanotube growing, it would be growing into a perfect cylinder. And nowadays, people can grow these literally by the million. This is what's known as a nanotube forest, where you've got a bunch of nanotubes growing from this surface vertically. And, well, how do I know they're nanotubes? I can look in with the electron microscope, and I see that this forest is made of an array of vertical objects, and if I look in closer, you can see that they're little tubules. Now, the diameter of that tube is about 2 nanometers. The length of those nanotubes is what? It's about 2 millimeters. Now, just to put, this is what we call an aspect ratio, i.e. a length to diameter ratio, which is phenomenally large. And to put it in context, if I had a nanotube that was, or a tube with the same length to diameter ratio that was this wide, and I held it like this, the other end would be in Manchester. So these things are really, really long and really, really narrow. They're the most elongated objects known to man. The other thing that's very, very useful about them is that experiments about 10 years ago where people were able to grab onto carbon nanotubes in an electron microscope and pull and break them showed that they're phenomenally strong, yet only about a quarter as dense as steel. And just to try to put their mechanical properties in context, this is a graph of strength versus the energy required to break, aka the toughness of a range of materials. These are plastics, these are metals, these are polymer fibres, this is the strongest fibre ever made, and these are carbon nanotubes. So these things are much, much, much stronger than any other material. So a carbon nanotube is 50 to 100 times as strong as steel, and yet only a quarter of the density. So these are really, really phenomenal materials. So when you have the forest, as I showed you before, what people realized quite early was that if you just simply grab the corner of that forest with a tweezer and pull, you can actually pull out sheets of nanotubes. And these sheets can be laid on top of each other to form sort of overlapping arrays that have quite interesting properties. Alternatively, such a sheet can be twisted into a fiber. And these fibers are really, really strong. They're so strong that they can be knitted or knotted. Now, that mightn't sound interesting, but previously it was virtually no sort of one-dimensional nano objects were strong enough to be knotted. And in fact, there's a test called the overhand knot test that if you tie a knot in a fiber and you break it and it breaks a knot at the knot, forgive me, then this is just a test for strength in textile science. Now, these fibers, people have put them into light bulbs, and by using accelerating testing, they've shown that a carbon nanotube light bulb lasts 50,000 times as long as a tungsten light bulb. I mean, that really goes to show how different these materials are from normal stuff. And this is a picture of the sort of sheet I showed you in the previous slide with droplets of water, grape juice, and cranberry juice on top. Now, the reason this is interesting is that the mass of the sheet of nanotubes supporting this droplet is 50,000 times lower than the mass in the droplet. And if that doesn't sound impressive, think about lying down and someone putting a weight 50,000 times your weight on top of you. Now, these things are really strong. So nanotubes are about 50 times stronger than steel, and people have shown that these sort of fibers are not quite as strong as individual nanotubes, but about 1/10 of the strength. And to put that in context, if we could make a 1 millimeter diameter fiber from these nanotube fibers, that could support a small car. So these things are really, really strong. So what I've tried to show you is that nanotubes are great, but the reality is that the last 10 minutes have been pure hype. They may have fantastic properties when they're on their own as isolated nanotubes, but the reality is you never get isolated nanotubes, or hardly ever. In almost all cases, nanotubes are found stuck together in what are called bundles. And the reason for this is that everything sticks together on the nanoscale, which is a bit of a problem, but a lot of research has gone to try and address this. So the problem is that these bundles have got no superlative properties. So for about 10 or 15 years, people have been doing a lot of research to learn how to debundle them, to get individual nanotubes from these aggregates. And this is where my research comes in, because that's effectively what I do. So simply speaking, the easiest way to do this is to take nanotubes. You can't see them, but a small quantity of nanotubes have been put in a beaker of water, and then you add intense sonic energy. So this is an ultrasonic probe. This is a bit like the probes that doctors use, except the power output of this probe is, well, A, it's at a different frequency, and B, this is 10,000 times as powerful as the sort of thing that you use to image babies. But you can see that when I put this probe in and turn it on, the liquid goes black. And the reason it goes black is that the nanotubes have been broken out of their bundles and individualized. And all these individual nanotubes are now absorbing light, and the thing turns black. The problem is that when I turn the tip off, well, when the tip was on, the bundles have broken up into individual nanotubes, but when I turn the sonication off, they stick right back together. So we've made some progress, but we haven't solved the problem. And it turns out that the solution to this problem was very simple. This isn't something that we discovered, but we did a lot of work to characterize it. It was found that if you just take your nanotubes, you put them in water, and you add a small amount of soap, what happens is the soap coats the nanotubes, and this stops the nanotubes from reaggregating. And one of our small contributions to this area of research was, while everyone else was using soaps, surfactants in the parlance, that cost, 300 euros per gram, we showed that fairy liquid does just as good a job. So what can you do with these dispersions? We've done lots and lots of stuff. I mean, we've been doing it for 10 years, so we've had plenty of time. But one of the things I'm going to show you is just super strong fibres. So this is an apparatus that is crude in the extreme, and this is the apparatus for making polymer, i.e. plastic, fibres that have nanotubes inside them. And this could be done in your kitchen. And some people say, well, gee, that's not science, that's very low tech. That's actually a good thing, because the lower tech these processes are, the more scope there is to scale them up and put them into industry. So this is very, very simple. We've got a bottle of a plastic dissolved in a liquid, and we pump that through a glass pipe and into a collecting bowl. And then we take our nanotube dispersion, we put it in a needle, and we inject it into that flowing polymer. And what happens is, when the nanotube dispersion is exposed to the polymer causes the dispersion to destabilize and collapse to form a fiber. The fiber flows down the tube and is collected down here. So just to show you, this is Karen, who's in the audience, loading up the syringe with the nanotube dispersion, which will then be injected into this tube where polymer solution is flowing. And what you'll see is, when she turns it on, this is the fiber. It is formed almost immediately. It flows down the tube. It flows in here. It goes into a bath where it flows around. You can see it coming out, and it's collected on these mandrels. We were a bit short on cash, so for mandrels we had to use overturned test tubes glued to the bottom of the basin. That was before SFI helped us out. I see Graham in the audience. So when you stop the process, you get these fibres, these wet fibres, collected in the basin. And when you dry them off, you get stuff that's just like black thread. Now, is that black thread any good? So you can look at it with the electron microscope, and you see that the black thread is actually quite nice, well-defined fibres. And if you go and zoom into the end, you look in at the end and look in closer, you can see carbon nanotubes sticking out of the plastic at the end. So that shows we really do have nanotubes in these fibres. Now, let's look at their mechanical properties. One of the things we did is that we measured the strength as a function of the fibre diameter. And what we find is a very, very strong diameter dependence. I won't bore you with the details, but we understand exactly why this occurs. And we find that for fibres below a diameter of a few micrometers, they become stronger than steel. Now, it's important to note that steel is much, much denser than any plastic. So when you correct for density, so adjusted to density, all of these fibres are better than steel on a strength per weight basis. And this just shows you an example of the mechanical properties of one of the better fibres. This is steel, this is one of our fibres, and this stuff is, our fibres are 3 times as strong as steel, many times as stiff, and many times as tough. So these materials really are interesting. Now, I talked about using soap, and for some applications you don't want to use soap because the soap gets stuck in there and it's hard to get it out afterwards. So a simpler way would be to use just a liquid, or in chemical terms, a solvent. Now, it had been shown that nanotubes could be dispersed in this solvent, but it wasn't known if the nanotubes could be individualized. So we repeated the work that had been done in a university, I can't remember which, in the States, and then we deposited some of this stuff on a surface, and you look at it with a microscope and you see you've got a large quantity of individual one-dimensional objects. And these are typically a nanometer or so high, so you know you've got individualized nanotubes. So this is done in solvents without any requirement for soap. Now, as physicists, although the physicists tell me I'm a chemist, the chemists tell me they don't know what I am, but as someone who was trained as a physicist, I have to ask the question, why does this happen? And this is the only really technical slide that I'll have. So we used a branch of physics or chemistry, depending on your point of view, called thermodynamics, and we were able to theoretically calculate how much nanotubes we could disperse in solvents. So the concentration given by this equation, I don't want to bore you with the details, but to translate it into English, what it means is that if you want to disperse nanotubes in the solvent and the nanotube must have the same surface energy. And surface energy is just a property of materials. You can look it up in a book. So that immediately suggested, theory tells us this, we can design an experiment to test that. We can sonicate nanotubes in a wide range of solvents with a wide range of surface energies, and we can measure how much nanotubes get dispersed and see is this equation obeyed. And as you can see, the solid points are the data, and the dashed line is what the equation predicts, and we get pretty good agreement. Now, there are data points under the line, and it's well understood why that happened. I won't go into it. Now, this leads us to graphene. And graphene is really the wonder material of the last 10 years. So as I said, people didn't believe it could exist, and then people showed it could exist, and then people showed it could do everything bar make tea. And the list of superlatives that graphene has gets longer and longer, but some of them are, it's the thinnest material known to man, it's the strongest material known to man, it's the stretchiest crystal known to man, it can stretch to 20% before it breaks, it is the highest thermal conductivity of any material known to man, it's the highest electrical mobility, it's the most impermeable material, not even helium atoms can go through it. This is just a list of the most well-known. If I was writing a complete list, I'd need a roll of toilet paper. Now, the reason this links in with what I was talking about previously is that graphene has the same surface energy as carbon nanotubes. So if you can take bundles of carbon nanotubes and by matching the surface energy of the nanotube to the solvent, you can make individual nanotubes, why can't you take graphite and using the same process get individual sheets of graphene? So this was a question that we asked, and we performed some experiments. And we found what we did was we took powdered graphite, which you can buy, and importantly, this stuff is really cheap. I mean, if you were paying $5 per kilo, you'd be ripped off. And that's important because, again, if you want to commercialize this stuff or use it for anything useful, it has to be cheap. Carbon nanotubes, on the other hand, at least the good ones, cost $1.6 million per kilo. So that's quite a big differential. So what we did was we used a sonication process to sonicate graphite powder in a solvent. You get a black liquid. The question is, does that black liquid contain graphene? So if you look in there and look at the electron microscope, you see you get very nice, well-defined objects that have straight edges. Now, straight edges don't normally occur in nature, certainly not for a good reason. And the reason you get straight edges here is because these are very, very simple systems which break along an atomic plane. Now, actually, you can do more sophisticated measurements, which were performed by Valeria Nicolosi, who's back in Trinity now after being in Oxford for a while. And she performed electron diffraction measurements that showed, without any doubt, that these are individual monolayers of graphene. You can also look at something called a dark field image, and this is quite nice. It's a nice image. It really shows how thin these things are, but interestingly, it shows that the edges roll up just like old paper that's been sitting in the sun. And the reason I thought this was interesting is that after we got this image, a paper came out in Nature showing that actually the curling of the edges of paper is a scale-free phenomenon and should occur at all length scales. So I thought that was quite interesting. So you can look in and you can look a bit closer at these sort of pieces of graphene, and if you look with the atomic resolution microscope, you can see individual graphene atoms in a structure that is exactly as expected. And some people I show this to think that this is a simulation or this is a model. This is not. This is an experimental image. Now, it has been filtered to remove noise, but this is an experimental image. And the graphene, as you can see, is really good quality, and most importantly, it's defect-free. Now, why do solvents work for graphene? Well, it's just the same as carbon nanotubes. If you get the surface energy of the solvent right, such as surface energy matches the surface energy of graphene, which is known to be around here, you get lots of stuff dispersed and exfoliated. What about soap and water? Well, you can take graphene, you can mix it with soap, you get black liquid, you look in with the microscope, and you get graphene sheets. So it works with soap and water as well as with solvents. Can you do anything with this stuff? Well, graphene with carbon nanotubes is the strongest material known to man. So one might imagine that if you put it into a plastic, it will make the plastic stronger. So using our processing technology, we could put graphene into plastics. These are composite films, and we could measure the mechanical properties. And what we found is that as you add graphene to a plastic, the strength increases linearly until at about half a weight % of graphene, you've doubled the strength of that plastic. You can also make fibres. This is a fibre of polyester, and polyester is, of course, interesting because polyester fibres are everywhere. We wear them. Clothes are made from polyester. Polyester fibres are made in the hundreds of millions of tons per year. So this is really a commercial material. So what we were able to show is, again, by adding less than half a weight % of graphene to polyester, you can triple the strength. Now, these sort of increases are important. We're not making super strong materials like the fibres I showed you before, but we're making appreciable increase in the mechanical properties by adding very small amounts of graphene. Now, think for a minute how much plastic is around there, around you every day in your daily lives. And think if you double the strength of that plastic, that means that for a given structural application, you only need half as much plastic. That's a very, very, very large saving. 300 million tons of polyester produced per year. It's a very, very large saving. Imagine putting this stuff into cars. You make it strong enough that you can make components for cars. The density is a fraction of metal, so you reduce the weight of a car dramatically. That reduces the amount of fuel that you consume, which reduces the amount of CO2 that you emit. This is a real application. This is not one of the sort of hot applications like fast transistors or stuff like that, but this is an application that has potential to really positively influence society. Now, that was graphene. Graphite is one layered material among many. It's just one, it's just the most well-known. It turns out there are loads of layered materials. The simplest one other than graphite is called boron nitride. And in boron nitride, you replace every other carbon atom in graphene with a nitrogen and every remaining one with a boron. So structurally, it's very, very similar to graphene, except because you've no carbon, you've got boron and nitrogen, the electronic properties are completely different. This material is an insulator. There's also a family of materials called transition metal dichalcogonides, which also are two-dimensional layered structures, except they're like a sandwich of two different types of atoms. The outer atom can be sulfur, selenium, or tellurium. The inner one can be a range of transition metals. And there's about 15 candidates here times 3 of these, which means that there are nearly 50 possibilities for these transition metal dichalcogonides. And that's useful because depending on the combination, these materials can be metallic or semiconducting. The semiconducting ones have band gaps that vary from about 200 MeV up to 3 eV. So these materials fulfill the entire gamut of material properties. And it's recently been shown that these materials can be used to make transistors that compare very, very favorably with silicon transistors. There are also hundreds of other layered materials. This is a very, very rich area of material science. But the problem is, up till always, it was virtually impossible to take these layered materials and separate the layers from each other to give you individual layers. So, can we use our method? Well, we take boron nitride powder, and indeed, as another test, molybdenum disulfide powder, and we sonicate them in solvents. Now, we didn't pick solvents at random. We use a combination of experimental preliminary experiments and what we knew about the thermodynamics of the system to choose the solvents. We sonicated, and we get, in the case of molybdenum disulfide, a black liquid, in case of boron nitride, a white liquid. The question is, do these liquids contain exfoliated individual layers of the layered compound? Well, if you look in with a microscope, you'll see you do indeed see these two-dimensional structures. And if you look in closer, you'll see this is an atomic resolution. These are effectively atoms, and you can see the atoms are arranged in a nice hexagonally symmetric pattern and are pretty much defect-free. And if you look even closer and do a little bit of filtering, you see you get almost perfect structure. These experimental images show structures that are almost identical to what you would see in a textbook. Now, one of the reasons this is important is that people have known for a long time that these layered compounds were useful in a number of applications, but one of the problems was that they're very, very difficult to process. So, for example, boron nitride can be formed into structures, but at temperatures of about 1,000 degrees centigrade. So, obviously that can be done, but it's not straightforward. Here, all we have to do once we have our liquids with our dispersed layers in them is we pour them into a Teflon mold, you go off, have a coffee, come back, the solvent has evaporated, and you have, in this case, freestanding films. This is a film of boron nitride, molybdenum disulfide, and tungsten disulfide. And this mightn't sound much, but this is revolutionary. This image was carried in, the paper was published in Science, but this image was carried as an illustration of the importance of this in Nature. Now, if you look with the electron microscope at the surface of these freestanding films, you'll see that they're just a disordered array of two-dimensional sheets. So, I mean, there's nothing fancy about them. One thing that is interesting, though, is that the solvents that you disperse these things in are the same set of solvents as you can disperse graphene in, or carbon nanotubes, or a lot of other materials. So that means you can take your dispersion of graphene, you can mix it with a dispersion of MOS2, and you can make a composite dispersion. You can then make composite films, which are, in this case, 50% boron nitride, 50% graphene, 50% molybdenum disulfide, 50% graphene, etc. And if you look with the electron microscope, you'll see that for the graphene molybdenum disulfide composite, it's just an array of sheets because the two components are just platelets. But if you do the same thing and make a composite with single-walled nanotubes and molybdenum disulfide, you'll see the flakes are embedded in a matrix of carbon nanotubes. Now, that's all very well, and you might say, well, okay, that's fine, you can do all of these things. But why do you want to do all of these things? Well, it's been known for a long time that a lot of layered compounds have huge potential in a lot of important areas, such as in energy generation and storage, except for one thing. Their electrical conductivity was just too low. And it turned out that that was a game changer. That meant that the whole deal was off. But graphene and carbon nanotubes are conductors. So if you put conductors into these materials, then you might increase the conductivity. And in fact, you do. This is a graph of the electrical conductivity as a function of the amount of graphene that we've put into these composites. And you can see we increase the conductivity from a very, very low level, increases dramatically by, I don't know, what is it, 8 orders of magnitude. And that sort of increase is more than enough to fulfill the requirements in areas such as supercapacitors, thermoelectrics, or other things. And nicely, again, as physicists, it's not just enough to show you can do it, you have to understand it. And this increase fits perfectly to percolation theory, both above and below the percolation threshold. So just to show you an example of an application, lithium-ion batteries. I'm sure everyone in this room has a laptop. And we all know that after a couple of years of having a laptop, the battery doesn't last nearly as long as it did at the start. And the reason for that is that when you charge a lithium-ion battery, you put lithium ions into the electrode, and then when you discharge it, i.e. you use it, the lithium ions come out. And then you charge it again, they go in, then they come out, in, out, many, many times. Now that process of putting the ions in and taking them out stresses the electrode material greatly and ultimately results in cracking. Small cracks mean that your battery life goes down a bit, big cracks means your battery dies. This has always been a problem. Now we thought that if we add carbon nanotube, and I should say molybdenum disulfide had been predicted as a lithium-ion battery electrode material in the 1980s, but the conductivity was a killer. So we thought if we put carbon nanotubes in with molybdenum disulfide, A, it'll solve the conductivity problem, and B, it might resolve the cracking problem. So we made batteries in collaboration with colleagues in Australia. These are what are called coin cell batteries. We measured the capacity, and we find that not only do the nanotube-filled composites have they much higher capacitance, but they're much, much more stable. And interestingly, this was our first go, and commercial batteries have capacities in sort of this region. So we're not that far off what's commercializable in the first attempt. So we were pretty pleased with that. So I said there were a very, very large number of layered materials. Well, here's just an example that we can actually exfoliate a load of different layered compounds using our techniques. And not just the ones I've talked to you, other ones, oxides and more complicated materials. So really, we've yet to meet a layered compound that we can't exfoliate. So finally, I've shown you a lot of materials and I've said they might be useful in certain areas. Can we translate that application potential into a commercial material? So the idea is to collaborate with industry. And this is done, and I have to say we're very, very lucky in Trinity. This is done through our Nanoscience Centre, which is CRANN, the Centre for Research in Adapted Nanostructures and Nano Devices. And one of the remits of CRANN is to leverage the research that goes on in the schools of physics and chemistry, and indeed other schools, to try and work with industry both to develop processes and even products, and also to support and resolve problems that industry might have. So the first question is, where can nanomaterials make a commercial impact? So there is one big problem looming, And this is the so-called transparent electrode problem. Everyone's got a TV, everyone's got a phone, most people have a laptop. On the front of any display, behind the glass, you've got an electrode that must be there to deliver electricity to the active material to allow light to be given off. But once that light is given off, it has to get out. So this electrode is transparent. But electrodes are metal, and we all know that metal isn't transparent. It's silver, or maybe if you're lucky, you might have a piece of metal that's gold. So how can you have a metal that's transparent? Well, it turns out that there are a small number of metals that are transparent. Indium tin oxide a conductor is probably a better word to use, is a conductor that's transparent and is used traditionally here. Now, one of the problems with indium tin oxide is that indium is running out. We expect that we will have depleted almost the entire global supply of indium at current rates in 25 years. Now, that I think is actually worrying. But in any case, that means the cost of indium is rising, and that's not good for industry. The second thing is that most people believe that in the future, displays won't be like this, i.e. on rigid supports. They will be on plastic supports that can be rolled up. So imagine a poster like a child will have in a bedroom that is actually a display that can show movies. So this is the future. Now, the problem with that is that indium tin oxide that's used in here, if you bend it at all, it will crack and it will break. So what's required, and this has been known for 10 years, is a new material to replace indium tin oxide that's flexible, low cost, and can be produced over large areas at low temperatures. Now, we were approached about 5 years ago by Hewlett-Packard to try and resolve this problem. Hewlett-Packard make a lot of computers, so this is a problem for them. And they set us targets for the optical properties, i.e. how much light the transparent electrode should transmit and what its electrical resistance should be. And more or less, they said, go and solve this problem. This was a big problem funded by Science Foundation Ireland. There were 22 researchers working for 4 years. That's nearly 100 man-years. This was a big project. We started off working with nanotubes, and this is a thin film of carbon nanotubes over the HP logo. You see it's thin enough that it's almost transparent. This is a look with the SEM, the scanning electron microscope on the surface. Now, what if we measure the optical transmittance of that film and the electrical resistance? Well, what you do is you make films with a range of thicknesses and measure transmittance and the resistance. Now, the problem is that thin films have high optical transmission but high sheet resistance, which is not what you want. Thick films have low transition and low resistance, which is not what you want. And in fact, there is no thickness that gives you a combination in this box which defines the industry requirements. And in fact, I have to say that there are probably approaching 1,000 scientific papers on carbon nanotubes in transparent conductors. And it just doesn't work and will never work. I won't show you today, but we were actually able here in CRANN to show why it won't work. So if carbon nanotubes don't work, then you need another material. So graphene is the obvious target. It doesn't work. So the solution to this was actually quite simple. Metallic nanowires. You can buy little nanowires that are a few micrometers long, made of metals, in this case silver. And you can deposit by spraying, which is a large area processing technique, networks of silver nanowires that are just the right thickness, just get you what industry want. And this, after 4 years, took us to the pinnacle, the state of the art in this area. And we're one of only maybe 3 groups in the world that can achieve these sort of results. And actually, surprisingly, the cost is not that high, simply because silver might be expensive, but the films are incredibly thin. Silver is also running out, but it's subsequently be shown that this can be done with copper. So it's all good. Now, just to show you, here is just a movie. This is a film of silver nanowires on a plastic surface. There's an electric circuit going into a power supply through an LED. When you connect the circuit up there, the light goes on. The current driving that device is flowing through this transparent piece of plastic. And when you bend the piece of plastic, the light stays on. If that was indium tin oxide, the light would turn out because the electrode would break as soon as it was bent. So this really shows that this does indeed work. Okay, second application, graphene. A lot of people believe that graphene is going to be used in a wide range of applications, whether it be reinforcing polyester t-shirts or whatever. Now, to do that, you're going to have to be able to make it in large quantities. And it turns out there are different ways of making graphene, but ours is probably the one that's most suited to scale up, well, certainly scale up of high-quality graphene. Now, what you want is to be able to make this stuff by the ton. Now, when we started, we were making it in vials this big, which is obviously not great. But now we can make them in vials this big, and we're collaborating a project that's just started last week with a British chemical company, Thomas Swan, and the idea is at the end of 2 years, we'll be at this length scale. So I'm really proud of this because this is something that we have invented, we have developed, and now is being commercialized and scaled up to industrial levels. Now, finally, you've been very patient. Finally, the last application is one that's very dear to my heart, I must say. It's about beer. So, beer comes in glass bottles. And the problem with glass is it's dense. Glass bottles are heavy. And with modern economies of scale, the ideas of local breweries are gone. Breweries are centralized, which means the beer has to travel long distances to the shop. Now, these glass bottles, actually the weight means that the amount of fuel that the beer trucks use is actually quite a lot. And you might think, well, that's not a big deal. For someone on the scale of SABMiller, which is the second largest beer company in the world, that is a big deal. So what they want to do is they want to put the beer in plastic bottles, the same sort of stuff as you get Coke in. Now, the problem is that carbon dioxide, the fizzy stuff in beer, leaks out of plastic bottles. Now, for Coke, that's not a problem because the taste of Coca-Cola is relatively insensitive to the concentration of carbon dioxide. But for beer, if you lose 10% of the carbon dioxide, the flavor is gone. So the shelf life of beer in one of these bottles is only about 2 weeks, which is obviously a big problem for them. So they've approached us, and we have a project that will start in the next month, where the idea is that we put our layered compounds into plastic, and these layered compounds act as barriers which make it difficult for gas molecules to get through. And theoretical modeling that we've done have shown that we should be able to, with small quantities of layered compounds, increase the shelf life of beer to about 6 months. And I think that's something that we can all be pleased with. So just to conclude, I believe that nanoscience is the gateway to new technology. However, to be able to do that, you need to be able to control nanomaterials. And once you can do that, and you've got applications, you can't just sit on them, you have to collaborate with industry. And that's something that in CRANN we're very, very fortunate to be able to do. Now, I did very little of this work. In fact, I ask people to do stuff and they do it, so I don't do anything. I have a team of about 15 people. These are people past and present, and these are the ones that must be thanked for all of this because it couldn't have happened without them. In addition, collaborators in chemistry that helped a lot, and also I have to thank the funding bodies because none of us work for free. So I was funded by Science Foundation Ireland and the European Research Council, and of course, thank you for your attention.
Thank you very much, Johnny. That was very good. So Johnny's agreeable to take a few questions before we take the beer. Peter.
You developed all of this intellectual property which has value, commercial value. How do we as a college benefit from that? How do you as a PI benefit from that?
Well, I mean, the first thing to say is that the development of the intellectual property shouldn't and can't affect the publication of academic papers, which is what we're all about. And one of the things that CRANN has done very well is to develop mechanisms where we have agreements with the industries that we collaborate with in ways to protect the IP without delaying publication. And it did take a little bit of time to get that right, but we believe now that we have mechanisms in place. Now, once you have the IP and you've published a paper, how does that benefit? Well, hopefully, I might get money out of it. But any money I get will only be a fraction of what the college gets out of it. So everyone's a winner.
But you'll license this?
Yeah. Well, I mean, there are a number of ways to do it. I mean, I don't see myself, this is something that others do, and that's great, but my own personal preference, I don't see myself starting a startup. So a lot of it will be licensing. In particular, the stuff that's funded by industry, then they will have the first right of refusal to license. But that is all agreed at the start.
Another question? John.
So that helium doesn't diffuse through graphene, which is quite striking. Does atomic hydrogen?
It's not, well, atomic hydrogen, I don't know that we know whether it diffuses or not, but we do know that under certain conditions, atomic hydrogen, when graphene is exposed to it, can bind to it to form graphene.
Oh, it is.
Is it known exactly why the graphene in the polymer strengthens the fiber?
Well, well, to be technical, it fits with, it's consistent with Cox's shear lag theory. It's just rule of mixtures type stuff. The stress is transferred from the plastic into the graphene, and that effectively reduces stress in the plastic, which means you can apply more stress before it breaks. It's nothing fancy. Although the interesting thing is that what that means is that continuum mechanics actually works down to the molecular level, which is actually quite cool in itself.
Okay, if that's all the questions, just want to say that the Faculty of Engineering, Maths and Science is hosting a reception downstairs, just one floor down, so you're all very welcome to come to that. The crowd may be a little bit large from the room, but you can sort of spread out into the landing around the stairs. Just remains for me to just ask you all to just thank Johnny again for a wonderful